price feed address. So we're going to have to add some type of parameter here. For now, let's just hard code it from our config, and we'll go into our config and we'll start our networks flag. We're going to be working, like I said, on the mainnet fork for this quick and dirty here. We'll call ETH_USD price feed. We'll grab the ETH_USD price feed from mainnet, since we're going to be doing a mainnet fork here. Pop that in here. Now we can just say from config networks network.show active ETH_USD price feed. Of course, we're going to need to import network here. And now we can do our kind of quick and dirty test. We can do lottery dot get entrance fee. Am I spelling that right? Get entrance fee. Yes. Assert lottery dot get entrance fee should be greater than, let's just go down one, 18. Or if we wanted to make sure we're actually doing this right, we'll do from web3 import web3. We'll do web3.2way 0.019 comma ether. Should be greater than, and then we'll even do 0.018 just to make sure, and it should be less than 0.022. Now these numbers are of course going to be a little bit different for you, and if you want you can go ahead and skip this part so that you don't have to do the math, but it is kind of nice to do a quick sanity check saying, okay, like based off what things are right now, what would this price end up to be? Now in our last section we made a mainnet fork dev network. I'm going to just go ahead and customize our mainnet fork the way that we showed you guys how to do mainnet fork dev. This way you can use accounts and we can be a little bit more robust here. To do this, we're first going to have to delete Brownie's internal built-in mainnet fork. So we'll do Brownie networks delete mainnet fork. Mainnet fork has been deleted. And now let's go ahead and add our own mainnet fork using Alchemy as our Ethereum connection. So you'll want to create a new app. I've already created one here called Smart Contract Lottery. We'll view the key, and this is the HTTP endpoint that we'll use. So to do this, we'll do Brownie networks add. This will be a development chain. We'll call this mainnet fork. It'll be a ganache CLI. The host is going to be our local host, so 127.0.0.1. And the fork is going to be equal to our Alchemy HTTP here. We'll do accounts equal 10. That way we can use the accounts. We'll do the mnemonic equals Brownie. And port is going to be 8545. And great, mainnet fork has been added. Now that we have this here, we can go ahead and run our test. Brownie test -- network mainnet fork. Whoops, looks like we got a little compile error on our math here. Whoops, it looks like we're divided by price when we need to be divided by adjusted price. And we forgot the parentheses on latest round data. Let's try this again. And I put an extra comment in here. Let's try this one more time. Lovely, and it looks like we're forking correctly. And awesome, it looks like our test indeed passes here. Of course, we know that we're going to want to change this because this isn't a great way to actually test our contracts here, but it can be a nice sanity check. And we know we're going to have to refactor this as well for mocks and for accounts, but we'll get to that in a little bit. Awesome, sanity check complete. Let's get back to our contract here. So we are getting the cost to enter correctly. Perfect. We're we're getting this entrance fee. What that means we can do in our enter function, we can do require message.value. It's got to be greater than or equal to our get entrance fee function. And if it's not, we'll give an error of not enough ETH. We have a way for them to enter, and we have a way to get the entrance fee. But we want to make sure that we're not ending the lottery before the lottery even starts, right? Or we're not entering a lottery when a lottery hasn't even begun. So we're going to want a way to iterate through the different phases of this lottery. And we can do that with what's called an enum or an enum. According to the Solidity documentation, enums are another way to create user-defined types in Solidity. We saw an earlier version of doing this with a struct. Enums are a little bit different in that they're explicitly convertible to and from all integer types. So what does that actually mean? Well, we can have an enum like this, action choices, go left, go right, go straight, and sit still. They're just more readable ways to say go left is going to be represented as state 0, go right is going to be state 1, go straight, state 2, sit still, state 3. So for our lottery contract, we're going to want to create this new type that represents the lottery state. So to do this, we'll do enum lottery state open, closed, and calculating winner. This means that we have a new type called lottery state with 3 positions, open, closed, and calculating winner. These different states are actually represented by numbers. So open is actually a 0, closed is actually a 1, and calculating winner is actually a 2. Now that we have this new type, we can create a variable of type lottery state. So we'll say lottery state, public, lottery state. And right when we initialize our contract here, we're going to want to set our lottery state to being closed. So in our constructor, we'll do lottery state equals lottery state dot closed. Now, since these are represented by numbers as well, we could also just do lottery state equals 1, because 1 stands for closed. However, it's much more readable to do lottery state dot closed. Now that we have a lottery state, in our enter function, we can require that the lottery state is going to be equal to lottery state dot open. So we can only enter if somebody's started this lottery. And that's exactly what we're going to do in our start lottery function. We're going to do a require in here that the lottery state is going to be equal to lottery state dot closed. And we can even add a failure function in here saying can't start a new lottery yet. And when we do start this lottery, we'll say lottery state equals lottery state dot open. Now, when somebody starts the lottery, they'll be able to enter. Of course, this start lottery bit here needs to be called only by our admin. So this is where our only owner modifier is once again going to come into place. We could write our own only owner modifier, or we can once again use OpenZeppelin's access control and OpenZeppelin's ownable function instead, which is what I'm going to use here. So we're going to go ahead and grab this, copy this, paste it in, import at OpenZeppelin/contracts/access/ownable. And of course, since we're doing this, we're going to have to add this dependency into our config. We're going to be using OpenZeppelin/OpenZeppelin contracts at 3.4.0. We're going to remap at OpenZeppelin equals this. Oops. And then we'll say our lottery is ownable. Perfect. Now we'll try to compile this. Awesome. Looks like Brownie grabbed everything correctly and we're good to go. Great. Now we can finally move into our end lottery function. This is where we're actually going to choose a random winner here. We only want the admin to be the one to actually end the lottery, so let's add the only owner modifier here. And let's talk a little bit about randomness, because this is what we're looking to do now. We're looking to get a random winner here. Now, as you know, the blockchain is a deterministic system, right? And this is super advantageous because it allows us to do all these smart contracts and have this system that can actually reach consensus very easily. Random numbers are much harder. If, let's say, you had a blockchain with a whole bunch of different nodes and each node responds and gives their own random value, well, each node is never going to be able to sync up and say, hey, we all agree on a random number. What you could do is you could base the random number on some other attributes in the system, but then it's not really random. It's actually going to be pseudo-random. So getting truly random numbers in a deterministic system is actually impossible. And if you know a lot about computer science, you actually know that even when you call like math.random in your JavaScript, what your computer is really doing is it's looking at some place in memory, grabbing some value and saying, hey, this is probably random enough. Here, go ahead and use this. Now, in smart contracts, especially when working with any type of financial application, such as a lottery, having an exploitable randomness function means that your lottery is at risk of being hacked or destroyed. And this isn't even a fairy tale. At the time of recording, about 2 weeks ago, I did a rundown on an exploit where a protocol used insecure randomness and got hacked for $700,000. So I am going to show you this insecure way first. And the reason that I'm going to show you is that it is a quick and dirty way to get a pseudo-random number, but please do not use this in any production use cases. I'm going to show you a method that's often used to teach people how to get random numbers, and then we're going to explain why it's so vulnerable and not a good method of randomness. And what some insecure protocols will do is they'll use a globally available variable and hash it. So in your smart contracts, there's actually a number of globally available variables. One of those, as we saw above, is going to be message.value, right? It's going to be the value that's sent with a transaction. Another globally available variable is going to be message.sender. You can actually see a whole list of these different globally available variables in the Solidity documentation here. So since there are all these globally available variables, a lot of times someone will see something like block.difficulty, which returns the current block difficulty. Now, one of these globally available variables is going to be block difficulty or block.difficulty. It's the current block difficulty. Remember how I said that the time between different block generation is called the block time? Well, you can always keep that block time as is by changing the block difficulty over time. The harder the problem or the harder the proof of work algorithm, the longer it's going to take, or the more nodes you're going to need to solve that problem. There's this constantly recalculating metric called Ethereum difficulty or block difficulty, depending on the chain that you're working on, that constantly changes. So you might think this would be a great use of randomness, right? Because it's a somewhat hard to predict number. So what a lot of people do is they think that, hey, those sound pretty random. Let's use them as a unit of randomness. And what you'll see is, like something like uint, Kachak 256, which is, again, this hashing algorithm. And they'll do something like abi.encode packed, nonce message.sender, block.difficulty, block.timestamp, mod, players.length. So I know there's a whole lot going into this line, and let's talk about it. So first, as we can see, is that we're casting or we're converting everything in here to being a uint256. The reason that we're doing this, of course, is because we're going to want to pick a random winner based off of an index, right? We're going to want to pick some random winner in our players array or our players list. So we say, okay, whatever number that we're going to use, that's going to be the index of the winner that we're going to randomly pick. Then they use Kachak 256, which is, again, our hashing algorithm. So they hash a whole bunch of variables together. And they do this abi.encode packed. ABI is another keyword for some low-level work. They'll add maybe a nonce in. They'll add the message.sender, block.difficulty, and block.timestamp. Basically, what they're trying to do here is take a bunch of seemingly random numbers, mash them all together in a hashing function, and then say, yeah, this is pretty random. But the issue here is that